Are you running? Okay, I'm going to be talking a little bit about our heavy duty and light duty worm blocks. In Shibumi, basically we've done a fair amount of development to get to a point where we can provide advancement from this type of an arrangement. This is a worm block for a Skywatcher EQ8, and that's a worm. That's the timing pulley that drives it. This is the mounting structure that holds it on the structure of the mount, and in use that would mesh with the thing I'm holding in my left hand, which is a worm wheel. You see it's covered by a red, fairly thick grease, and this one has 435 teeth. It's 10 millimeters thick, it's made of aluminium, and basically every time the worm rotates one full rotation, it moves this wheel by 1/435th of a rotation. And in use, those two are meshed like that. You can see that the wheel is mounted on bearings and it rotates on a shaft. This particular one is the right ascension shaft, the one that basically tracks the stars. And there's one shaft bearing installed and there's another one kicking around elsewhere. This particular shaft is made from aluminium. It's turned from solid bar. It makes it a relatively light assembly, although aluminium is obviously not as stiff as a steel would be. There are various issues basically with the EQ8 worm gearing, and essentially the same system is used for both axes, exactly the same wheel, a very similar worm, the same driving motor is used, which is a two-phase bipolar stepper with 400 steps per revolution, mounted on a rubber isolation coupler, which is this plate-like object here. And there is normally a timing pulley on the end, and a timing belt would normally be used, which connects the two, and when tensioned it transfers drive from the motor to the worm. But that's the normal way these things are done. There are many problems with this though. The most obvious one, I suppose, is that with time and wear, the worm, this is the worm removed. The worm, because it's not made of a stainless grade of steel, it can corrode. Now, while mostly it's, at least the working surfaces are covered with grease, and that's not going to be a problem, it's something that need not be this way. The bigger issue is the bearings, which are really rather light duty for the capacity of the mount. These are type 608 bearings, which are, I suppose, better known as skateboard bearings, and they're inclined to have their races indented by axial loading. So if somebody drags the telescope mounted on the mount around without releasing the clutches, there is at least the possibility that you can overload the thrust capacity of the bearings. As you drag the mount around, basically it transfers drive backwards through the transmission, forcing the worm to basically push against the bearings that provide axial support, with fairly negative effects for the rather light duty races in this type of a bearing. So that's one issue, basically, general durability and a tendency to corrosion. There are other elements in the drive system that can also be an issue. The OEM type of timing belt and belt pulley is what's called a HDD type tooth pattern. Now, this type of belt and timing pulley is not designed to be zero backlash. You can approximate zero backlash by having your pulleys designed in a certain way, but it's never going to be genuine zero backlash. It'll be an approximation. Why does backlash matter? If you're doing imaging with the mount, particularly if you're doing auto guiding on the declination axis, it's normal to expect the corrective motions of the declination worm to be very small and often in opposing directions. So you make a small correction, then you do nothing for a while, then your auto-guiding software will call for a correction and you may find you have to reverse direction. And when you do that, that's when backlash, either in the timing belt that's driving the worm, or indeed in the fit of the worm flanks into mesh with the wheel, would be relevant. Any clearance that you have there is going to show up as backlash. That's quite apart from what we said earlier about the light duty nature of these bearings. Lack of stiffness in the bearings, even when actually preloaded, basically means that if the worm shifts axially more than a micron or two, that's something that's going to be perceptible in your auto guiding, and ultimately in the quality of the star images, in the images that you take if you're an imager. For visual use, it's not likely to be an issue. So this is a declination axis worm block and support bracket taken from a Skywatcher EQ8R in this case. And there's a very similar arrangement used with a very similar worm on the right ascension axis. It's the same profile, it's the same module, 0.5. In this case, you have a black component appears here, which is a little optical flag that's used to signal to the mount controller whole rotations of the worm by means of a little slot, which you may be able to see there. And that slot basically is used to allow passage of a light beam, which signals to the controller whole rotations of the worm. And this can be used for periodic permanent error correction if you want to do that. Now, the biggest issue with both the right ascension and declination worm blocks on this mount is, and has always been since the mount first appeared, the fact that it wasn't designed with backlash compensation. This is not anti-backlash gearing. This is what's called fixed centers gearing. And all that means is that the relative position of the worm and the wheel axes are fixed relative to each other. They're fixed by being bolted to a large block of aluminium that is either the right ascension or the declination housing. Now, what's wrong with that, you might ask? Well, if you have fixed centers and it's a cold evening and your mount basically contracts down because all materials expand and contract to some extent with temperature changes. If you're using an aluminium gear, even in an aluminium housed mount, you are going to see variations in the clearance, the mesh clearance between the worm and the wheel. Now you might think, well, how significant a factor can that be? People who image with this mount will tell you that it's perfectly normal to have to basically adjust the backlash when imaging in winter and in summer, and in some cases more frequently than that, depending on what your environment is like. At the very least, it's a frustration to have to do that, and it's not a particularly easy adjustment to make. So most of the better quality mounts these days would have some form of backlash adjustment if they're worm gearing based. What my company has done is to develop adaptive backlash compensation, which is what this assembly is. So this is our equivalent of the original mount manufacturer's declination worm block, and as you see, it's a little different looking. We do two versions. We have a light and a heavy duty version. This one happens to be the heavy duty version. In use, as with the original equipment manufacturer's design, you have the step motor mounted here. You have a timing belt drive. We've added a tensioning pulley, which is important for our design, but it wouldn't have any great effect on the original equipment design. And that then is tensioned by moving the bracket and locking it as you need to. You will notice the timing belt is not the same as theirs, and the reason for that is we have opted for a genuine zero backlash type design. This is a GT2 type timing belt, and the pulleys are a little unusual too. They're GT2, they're precision machined, and in the case of the motor one, it has a split clamp hub rather than set screws. Apart from marrying the shaft that they're screwed onto, set screws can in some cases tend to cause a little bit of decentration of the pulley, and generally for instrument type work it's better to use a clamp hub or a shrink fit if you possibly can. So for the motor pulley we use a clamp hub, as you see. On the worm end we have obviously the same toothing. It's a larger pulley because this system is designed to give a 1.5 to 1 reduction in order to boost the torque of the drive. But this pulley is actually shrink fitted onto the spindle of the worm. Now the worm that we use, and we produce these ourselves, looks like this. This particular one is a 400 series grade of stainless steel, which is something that's capable of being hardened and holding a reasonable level of hardness. It's physically bigger than the original worm. You're basically trying to resist bending and also looking to basically move larger payloads without departing from the original gearing specification, which, as I mentioned, was module 0.5, which is fairly fine pitch toothing. And this has a pitch diameter of 19 millimeters. The wheel that it mates with, you can mate it with various wheels, but in the Skywatcher EQ8 application, you're mating it with a wheel that has a pitch diameter of 218 millimeters. So basically that meshes very nicely with the original worm wheel, or if you're using our heavy-duty worm wheels, which has the same type of toothing, but is a thicker, heavier duty wheel, it'll mesh nicely with that as well. The other thing about these that's notable is that these are precision thread ground. EQ8s out of the box, as you buy them, normally will have a periodic error, that's to say intrinsic transmission error of the worm of 6 arc seconds peak to peak or less. Very occasionally you might find one that's a little larger than that, and frequently they would be less. The ones that we offer, the standard grade ones, have a 4 arc second peak to peak measurement, and they're individually tested and certified using a double flank testing rig. We also offer a research grade worm that's guaranteed to have less than 2 arc seconds peak to peak axial transmission error. So this part is non-corroding and is quite durable, and basically it is burnished in mesh with a sacrificial worm wheel, and these are fitted to worm blocks, as this one has been, and it can be seen in there. The bearings we use are obviously a little different as well. You can see the difference between the OEM style 608 skateboard bearing and this needle roller design, and that runs directly on the worm. There is no inner race. It runs directly on the worm with about a 10 micron clearance, and then at the back end here there is a ball thrust bearing built into it which takes the thrust loads. Now the overall load capacity of a bearing like that is very substantial. So in normal use, you can see the worm basically has spring loading at one end. We use disc springs of a calculated stiffness to preload the bearings and make sure that there can't be any axial shifting, either due to temperature change or minor amounts of wear or very heavy loading. So this is a much more instrument grade type approach than the highly value engineered approach used by the OEM. Now this worm block is a little odd. If you look at it here, you can see that it has, see if I can point with something, it has slots in it. It's actually slotted all the way around. And the reason for doing that is that this worm block is flexural. There are two adjustments in this assembly. There's a sliding adjustment like this, which can be locked by clamping these screws. And this allows the worm to be brought into mesh with the wheel, and then you lock it down. What you can then do is make micro adjustments using this central screw and a opposing spring on the opposite side. And by making micro adjustments and by reference to a scale that's a little hard to pick up, but it is there, you can actually set the meshing force. You can probably see that moving there. So what that lets you do is set a very consistent meshing force between the wheel and the worm. And once set, that is very stable. And as the worm expands and contracts with temperature, and as the worm changes its dimensions very, very slightly with wear over extended use, that spring-loaded meshing ensures that you still maintain stable zero backlash conditions. For reasons of durability, obviously it's important to pick suitable lubricants for the bearings and for the actual sliding surfaces. We've had good results with a extreme pressure lubricant with molybdenum disulfide additive in it between the worm and wheel, but there's absolutely no reason why you have to have that. You can also use a damping lubricant as the original manufacturer has used in this case, and that works extremely well. There's no reason to actually change that in our opinion. The lubrication in the bearings in the worm assembly is basically designed to be serviceable down to at least minus 25 degrees, and we can also offer to special order a lubricant that will go to lower temperatures than that if need be. So basically this whole assembly then is designed to be a bolt-in replacement for the original bracket and worm, and it is a very capable upgrade for an EQ8 mount that's used for imaging with higher payloads. If you need to remove backlash and have a more precise lower periodic error worm, but you don't need to move large payloads, it's also possible to have a light duty version of this. Now that's something which is not exclusively performance oriented by design as this was. That's something which has been, to some extent at least, cost optimized, and for a lot of people that makes more sense, particularly if you're actually using your EQ8 as a transportable mount rather than a permanent installation. The same technology is used in the right ascension version of the worm block. These are approaching the end of the production process. All the worms are individually laser marked with numbers that let us basically relate the worm to its test record when we test it on our double flank tester. And at the end of the production process, we will clean this up, remove the marks and put a proper label on it with the date and a serial number, so that there's an audit trail of how the worm tested and was built. So the right ascension one looks a little different, not very different. The pulley is very much the same. It's preloaded with disc washers as before, but here you have this gap sensor for triggering the worm index switch, which is used if you're building a periodic permanent error correction table, which is something that the mount facilitates. And this bolts directly onto the lower end of the declination housing on an EQ8 telescope mount. Here is the declination axis heavy duty worm block that we looked at earlier, mounted now to an EQ8 mount that we're building. This mount might look a little unusual. This one has two saddles, not one, and no counterweight bar or counterweights. This is our twin saddle mount, but it serves to allow me to explain what it is we do. So the worm block basically is bolted onto the surface of the declination housing, which is this large black lump of metal here. And what we have in here, where I'm pointing, is the declination worm wheel, which you may be able to see. At the moment the worm is sitting just above the level of the wheel, and by adjusting the screw I can gently pull the worm block down until it engages. You hear it now, it's engaging with the worm wheel, and as I continue to pull it closer, pull the gearing centers together, eventually get to the point where there's no perceptible clearance. And now what we do, moving around to here and looking at the load indicator on the side, and I should be wearing my glasses but I'm not. What we can do is refer to the load indicator, and by adjusting the single screw we can set an appropriate amount of preload using this flexural block. And having done that, then we can lock the block so that it isn't going to move. And there's a screw, in fact two screws, that allow us to do that. That's one of them. There's another one in here, which I'm not going to move at the moment, but that's normally done with the belt removed. And once you've done that, basically you have a preloaded backlash-free drive system. And as you see, the motor is mounted in the same location as in any other EQ8, and you run the cabling in the same way to the interior. Beyond that, the details are very different on this mount because it's clearly a twin saddle design with a much longer shaft that connects the two saddles together. But normally you would mount your controls PCB in here and the other electronics and connect it up. So once you've done this, basically what's normally done is to use a piece of software to run the mount, oscillating like this, where you move X steps in one direction and about 0.9 of X steps in the opposite direction. And you do that for a number of hours, and that has the effect of marrying the worm to the worm wheel. The process is called burnishing, and it causes no harm to either the new worm or the old wheel, or if you're using one of our heavy duty wheels, the new worm and the new wheel. What you're doing basically is a very similar process to what used to be the case some years back when you would run in an engine on a new car. You would drive it at various speeds under different loads and basically break in the surfaces that slide together. So it's a very similar process. And what that tends to do is to improve the torsional stiffness of the drive, which has the effect of further reducing the residual levels of backlash that there are. And it smooths everything out. So that's how the thing works. There's no maintenance required in normal use. Theoretically, if it's seeing a lot of service, maybe chasing satellites or something like that where there's a lot of slewing, the lubricant ought to be looked at every other year and probably changed. That's not difficult to do because, again, you can mesh and reset the mesh using a single screw by reference to a scale. It's very quick to do, and in every other way this resembles the design of the standard Skywatcher EQ8 parts, but much stiffer, much more precise, a lower periodic error worm, and essentially this is designed to move heavier payloads.